Today we finish here, I think. No? Yes? So I told you that the fermionic action, we construct the Wilson action for the glue, and the fermionic action was obtained by the naive discretization plus a term, a Laplacian term, introduced by Wilson also. He made everything. And I, to avoid the doubling problem, the fact that in the lattice we had, with the naive discretization, 16 fermions instead of 1. So this is the very beginning of everything. Then there are several improvements to that. The one we will find the resource is the so-called Clover term. It's called Clover because, look, doubters, if you are able to pronounce that, then so people said Clover. So they add to the usual action an additional term to improve the discretization effects. Okay. And then there are other things you will hear about. Staggered fermions is very complicated but very fast. The domain wall I will not talk about. Ginsburg-Wilson is the best way to do it, but it is so expensive that nobody do it. And then this essentially Italian suggestion, very interesting, the so-called twisted mass. Okay, this was for yesterday. Also, you remember that the key element of all the computations is the quark propagator, is this animal. A quark created on some point and propagate and is annihilated at another point. And it is computed by summing over all the configurations the determinant times the inverse of the matrix. In practice, the determinant is absorbed in the density distribution of the configurations. So it's very interesting to see how one can compute a determinant of 10 to the 8 times 10 to the 8. It's certainly not by Kramer. The trick is the following, that you can always obtain a determinant of a matrix in this way. So you take phi is an arbitrary field, a dummy field. So phi dagger, phi the inverse of the square root of a dagger. And if you compute that, you compute a determinant. You can believe that this is more complicated than that, but it is not the case. Imagine a determinant of 10 to the 8. Okay? So it's more easy to generate this determinant by that. This is random fields. So you take in your computer this scalar random fields, and you sum this quantity, and it has the same effect than the determinant, and you include it in the distribution of the metropolis series that generates the U. So this is very tricky thing. Okay, now the last thing is that this determinant has the effect of letting a gluon to be materialized on a QQ bar pair. So if you have only gluons, but you have this determinant, then there are QQ bar pairs there. If you put in your simulation that equal 1, these are the so-called quench simulations, which are until 5 years, everybody was doing that. And when you take into account this determinant, these are the simulations are called unquenched, or also dynamical. And when we used to say the unquenched simulation with NF equal 2, 2 plus 1, 2 plus 1 plus 1, depending on the number of quarks that we let to create. So NF equal 1 will be that we have only U bar, and F equal 2, U bar, DD bar, and then with S and so on. Okay? So these quarks, QQ pairs, appears everywhere. Everywhere you have a gluon. So this is a propagation of a quark and antiquark. And everywhere you have a gluon, you can have these QQ pairs. Okay, so this was the... I also show you how that this Dirac matrix is practically empty. And this makes possible to obtain an almost perfect scalability when we use, for example, 400,000 parallel computers to make the calculation. So it's really linear. And that's all. The typical size I already showed you. Let's now very briefly how to compute observables that I'm going to show you. For instance, if we want to compute a meson mass, we put at some point at 0, we create a u bar d. So we take this operator, u bar times d. So u bar is like that and d like that, so it's a scalar. We create it here. And then we annihilate it at some point x, and we look for this correlator. And when we sum over x, the only variable that remains is the time, and we obtain the arma fatale, the Euclidean correlator that we know how to compute. So this will give us the mass, because it's an Euclidean correlator, it will give us the mass of the particle that propagates from 0 to x. On another hand, when we develop that, here are two quark fields, here are two, we obtain a vacuum expectation value of the product of 4 fields. This, according to the Wick theorem, is always reducible to the contractions. It means to that dd bar and u bar. But this is by definition the u quark propagator, remember? And this is by definition the d quark propagator. That's why whatever you put here, at the very end, you have always and only the quark propagators, more or less combined. So at the end you obtain the quark, the propagator of the quark d from 0 to x, the propagator of quark u, dagger, from 0 to x, plus gamma 5, and blah, 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 whatever you want, and a trace. And this is the key point. Imagine that you replace a meson by a baryon. You will obtain 3 quark fields here and 3 quark fields. So you will obtain a vacuum expectation value of 6 quarks. Doesn't matter. Wick theorems tell you that is at the very end you can obtain the result only as a sum of contractions. It's called contraction, but it is a contraction. Is a propagator in the Wick theorem. So that's why the quark propagator plays a very important role, even if it doesn't exist, because a quark doesn't propagate. But the mathematical object is defined. So now you can say, but okay, but a meson is not only a quark and antiquark at some point, and you are totally right. It's more complicated. There is some abstractor. So to improve the result, in fact, we introduce what we call a smeared. So instead of a quark field at x, we replace by a big quark field, a smeared quark, which is a sum of some partial distribution. So we make a kind of instead of a delta function at some point, we make a kind of, to mimic a kind of wave function, if you want. This is called the smear procedure. all that is well explained in my personal notes I gave to you, and maybe you get it in chapter 3. So it is, but here I didn't detail it. But it is a very important point because a meson is not only a quad and antiquad at some point, it's something more complicated. But we put some object that has the same quantum numbers of the state that we want to study. That's all. And this object is called interpolating field. I don't know what is the interpolation, but it's called the interpolation field. So this is the first remark concerning this point. The second remark, if I do not forget, do not forget that, because then, yes, the second remark is that there are some mesons, or there are some baryons, there are some states that they are not bound states. For instance, most of the mesons that Professor Pennington talked about are decay. So, in fact, and for these states, as well as for some nucleon excitations, for instance, the Roper, they decay very fast. So it is not really a system QQ bar. You will see in the results that we have serious problems to reproduce these excitations that can decay. So in this case, we have to make the correlator not only by some state like U bar D, but by a family of states, because the physical state is a combination of that. For instance, G0 can be U bar D, okay. But if it is a meson that can decay into two mesons, we have to take into account also here that it can be meson 1 times meson 2, so this is a 2 quark already. If it is a D meson, it will be a D meson is a C, I think. U and C, D, I don't know. So we have to put not only U bar D, but all the decays products. This is relatively new. We have been obliged to do it because the results fail, as you will see. And the conclusions are not yet well established. It seems that it improves the result, but so in this case we have not only a correlator but a matrix of correlators. And then one has to diagonalize this matrix to disentangle the different channels. Okay, so this is, I think, is the last remark on that point. Yes, it's meeting the gauge field. Okay. So, for a meson, once we so in the lattice we compute this because we have already computed the quark propagator. This is the only thing we need, and we know that it contains the mass. How we extract? We take the logarithmic derivative of this correlator, and this is called the effective mass. And you will see how fantastically good it is for the mesons. So this correlator, at a small time, it is not at all a constant, because in fact, in the exponential, there are other contributions. There is a sum. And so we have the ground state, but we have also the excited states. And we have to wait an hour's time in order that the excited states exponential are killed. And we have only the ground. And after some time, you see a perfect plateau, is fantastic, which goes very, very far, until 200 times. There is no any need, but it's just to show that for the meson, it will not be the case for the baryons, but for the mesons, we can have an incredible accuracy. So this is the size of a pion, a spatial extension, L32 cubed, and on time 256. Now, for the baryons, it's the same. It's just a bit more complicated, but the philosophy is the same. You create a baryon here with a combination of quarks, U, D, D, if it is a proton or I don't know what, a neutron maybe, U, D, D, I don't remember, okay. And then you annihilate it there, so it's exactly the same. The only thing is that you have 6 quarks, but using again the Wick theorem. At the very end, you need to compute only the quark propagators, and you extract the baryon, the nucleon mass in the same way. You can understand that this procedure can be extended not only to nucleon, but to 2 nucleon, to 3 nucleon, because if I want to obtain the alpha particle, it means 12 quarks. Okay, so we put 12 quarks here, 12 quarks there, a lot of contractions, and we will get the binding energy of the alpha particle. And I will show you some results, preliminary, because but it can be really generalized. The only problem, okay, this is the result, that if we don't smear, we don't apply this technique, the plateau is reached very slowly. So this is for the nucleon. And if we apply this technique, we have it already at 5 or 6 Euclidean time, we have already the mass of the nucleon. So it's a very important thing. Now, contrary to the mesons, the baryons start being nice, but what we can estimate is down in my notes that the signal to noise, it goes to 0 exponentially with a coefficient which depends on the nucleon mass minus 3/2, this is 3/2 of the pion mass. So this is always positive. So at the very after some time, the signal to noise start being terribly bad. And this is one of the limitations. If you want to do a nucleon, we have to go fast to the plateau, because if you continue, you start reaching an uncontrolled signal to noise region. So, and if instead of computing a nucleon, you compute a deuteron or helium-3, this is multiplied by A. So the region of the plateau is shortened exponentially. So this is the kind of problems we have. And now I'm going to show you. I have results for everything, and you will tell me what do you want. This is like a supermarket. I will start with spectroscopy. Well, for mesons, I've already shown you the quality of the correlators. It's fantastically good. This is you know already. Well, this is a kind of summary of the most familiar mesons. So for the pion is perfect. Even for the pion 1.3 and 1.8 or I don't know what, 9, the radial excitation of the pion are perfect. Have 2 parameters in the theory. For the rho, it's more complicated because rho is a resonance. So this is really tricky. You cannot say it's a stable particle at all. We have to take into account that it is a 2 pion. Exactly that. We have to mix always in the channels, in the initial and in the final channel, pi and row. When we do that, things are reasonable. If it not, you can find whatever you want. Row excitation as well, fantastically. For Keon, so we introduced a strange quark for the excitation and so on. Here, the eta and eta prime is complicated for a reason that I didn't tell you about. Is the fact that when you compute this propagator from 0 to x, QQ bar, the Wick theorem tells you that you can have the contractions, but you can have also a 0 to 0 propagator, the disconnected diagrams, what is called, and the x to x propagator. X to x, so loops like that. So you have to compute an x to x propagator, and this is very expensive. I told you that the propagators we compute are always from 0 to something. And this requires the full inversion of the matrix. And the full inversion of the matrix is n times a linear system, but n is 10 to the 8. So it's 10 to the 8 more expensive to compute that than that. So these stupid loops are extremely expensive. And people start developing a way to compute that, but you see there are very large error bars in the mesons, like for instance pi 0. Pi 0 is eta as well, but pi 0 you have the same quark here than here. It's the same QQ bar, it's not QQ prime. So you can have that and that. And for pi 0 we are not able to compute it because these loops, I mean, we start being able, but error bars are very large. But in general, you see that it is fantastically good, even for excitations. So we can spend a couple of days just with mesons, because we have, for instance, all the spectroscopy of charmonium, which is very exciting. Some states are always decaying, so it's very, very rich, but I made another choice and go to baryons. So I will first present some result in which I was involved, so the ETMC, which reproduce the baryon octet, so the nucleon, the delta, despite the fact that it is a broad resonance, the K, lambda, sigma, so all the octet. This calculation at that time were the best, and now it's already down. But it's interesting to understand what we compute and what we wanted to obtain. In fact, we compute the mass of the different baryons. This is the nucleon, this is lambda, sigma, and so on. Xi, well, as a function of the pion mass. We were unable at that time to simulate with pions smaller than 300 MeV. So this is 300 MeV pions, 280 it was. Okay, it was the record at that time. So we compute the mass of the nucleon and the baryons as a function of the pion mass, and then we were obliged to extrapolate. Then, in this case, the chiral perturbation theory tells us how a nucleon and the baryon behave as a function of the pion mass. So using these formulas, which is the chiral expansion, perturbation theory expansion, we could extrapolate to the physical point and give a prediction for the states. In fact, nobody knows if this chiral perturbation theory converges and what is the conversion radius and so on. But when you have nothing else, you do what you have. Now people are able already to simulate at the physical point. and I will show you some results. So the quarks we put in the lattice are really the physical quarks, has the physical mass, even below. Another very interesting result is the fact that, imagine for this is the nucleon, okay? So we make, I have to tell you that there is a relation, I don't remember the name, saying that m pi squared is in fact proportional to the quark mass. So when we have m pi equals 0, the mass of the quark is also 0. And we can see the effect of the quark masses in the nucleon. So we have just to extrapolate this and do not stop here, but continue to 0. And if you do that, you see that the nucleon mass is practically unchanged. It will be here. So instead of having, if we remove the mass of the quark in the nucleon, instead of obtaining a nucleon of 940 MeV, we will obtain 900. So 5%. So the quark mass itself accounts only for 5% on the nucleon mass. So when we said that the Higgs meson is the origin of the mass, we have to always to keep in mind that it is not true, because a nucleon, if you remove the quark mass, it's practically unchanged, 5%. Electrons will have no mass, okay? And of course, the world will be very different, because if electrons have no mass, you will not be able to attach it to an atom, so no atoms, a real disaster. But concerning the mass, it is not true that the origin of the real mass, the other one, we are still waiting. I mean, the dark matter and so on, we are still waiting for that. But for the mass that we really know, the Higgs particle is not very important, very relevant. I will show you that we can have something which is 1.5 times heavier than the nucleon, a glue ball, which has no quarks at all, and nevertheless is heavier than the nucleon. So Higgs, what is the role of Higgs here? Okay, now the best result we have now is obtained by this collaboration, like Budapest, Marseille, and Wuppertal, in which I am now involved, who obtained for the first time a final result, how to say. And well, of course, they had no this error due to the extrapolation, so they could obtain a very good description. And since that time, at that time they obtained pions of 190 MeV, and since that time they succeed to obtain simulations with 120 MeV pions, lower than the physical ones. So we can play with nature in the lattice. Just to show you that there are now several groups that are reaching the physical pion. Even ETMC with NF equal 2, they publish just on a proceeding, but also they claim that they have the nucleon with m pi equal 130 MeV. So this is the nucleon mass as a function of the pion mass squared. And they have this point, this is the experimental one. This point corresponds to a pion of 130 MeV. So this is not only a game, because sometimes we want to compute the derivative at the physical point. If you want to compute the derivative, it's better to have 1 point after and 1 point before, and then you make the difference. So there are some quantities that for which the derivative is essential. Well, also, okay. Also another collaboration, because it's always a delicate problem to know. This is QCD SF and UKQCD that obtain This is the nucleon as a function of the pion square. This is the physical point, and these are pions that are practically at the physical point. This is a summary of a lot of collaborations. Different collaborations differ in the different discretization of the action. What I show you, clover, staggered, twist mass, patati patata, and it's very, very important, the consistency. And indeed, this consistency exists. There is no doubt that the physics is the physics of the continuum, because so from this point of view, the result is perfectly well established. So really QCD reproduced the barium spectrum. This is because I told you that I will show you some result with 120 MeV. Is this one. It's from a guy in Saclay who is doing the PhD. This is a very private communication, forbidden, so I will remove it. But just to show you that we can have this. This is the physical point. And, well, and you see again that if the quark mass is 0, the world continues to be as heavy as it is. This is also a summary of different collaborations, so I include not only the mesons, but also the nucleons, the lambdas, sigmas, so it's very impressive. I mean, it's very impressive and very new. I mean, it is 3 years ago. And in 2009, the situation was really very different. So the improvement is fantastic. Now, I'm going to show you something that is, for me, is very interesting, because not only are able to reproduce the baryon spectrum and the meson, the ground state, but we are now entering into the accuracy era. Here is an example of the difference, mass difference between proton and neutron. You know that neutron is heavier than the proton. If it was not the case, the proton will decay into the neutrons, and we will not be there because there will be no atoms at all. If the atoms need a charge, so the fact that the proton is heavier, or the neutron is heavier than the proton, it is very helpful, but it's a bit mysterious. Because naively you could expect that proton with the electromagnetic field around will be more mass because it has the mass and so on. It will be a real disaster because... So these guys compute from first principles the mass of the neutron and proton. And they did it by breaking the isospin symmetry. You know that the quarks, we have two quarks, U and D, and they are different, but very different. I mean, a factor 2 on the mass. This is a very ugly situation. Why nature appears like that? Why it's so asymmetric? So on the level of the Lagrangian, on the Lagrangian is very unsatisfactory, at least for me, is factor 2. One is 3, the other is 6, or something like that. And this is the origin of this difference of mass. It's very interesting. So in the calculation that these guys, this is also BMW, they put MU and MD different. So, and also, they incorporate QED. So not only they break the isospin symmetry, but in the Lagrangian, they take into account QCD plus QED. This is terribly complicated because QED is an infinite range theory, the Coulomb interactions. So how to account on a small lattice of 3 Fermis, the Coulomb effects, which are long range. is not trivial at all. So this merits deserve already 2 seminars, but I will give you just the result. This result I take it from a PhD in which I was involved, and it has been published now with a small modification only in Science. It is in the web. So look the result. So of course it was done for all the variants, nucleons, sigmas, psi, kaons, and so. The most interesting case is of course Mn minus Mp, which governs the weak decay and the stability of the nuclear shard. This is what I told you, no? And in fact, look, for the nucleon, this is Mp, so I call delta M, Mp minus Mn. So the experimental result of this difference, Mp minus Mn, is negative because Mn is higher, okay? But we define it like that, okay? So this is the experimental result. And this experimental result is the result of two opposite effects. One is the QED. So this, if we let just the QED, indeed the proton will be heavier than the neutron. But when we introduce the QCD and the mass difference between U and D quarks, if the quark mu equal to md, then this effect will be 0. But because of this difference of mass, the total effect is larger and the opposite sign of the electromagnetic interactions, and that makes the neutron heavier. So this ugly symmetry breaking of the quarks at the level of constituent quarks. I remind you that the constituent quark mass is a misery with respect to the nucleon one, and it is nothing. But they are there just for that. To correct somehow the electromagnetic interaction that will make the proton heavier. Is very interesting and is also exceptional. If you look at another baryon, sigma, for instance, the sigma baryon has also U, and in this case, this is the experimental result. In this case, the QCD, when I call QCD is the effect of mu different from MD, and the electromagnetic are on the same direction. Here, so in fact, well, nothing changed dramatically. And for the Xi, also on the same direction. The only baryon that behaves on a foolish way is the proton. And to correct that, the mass difference between U and D plays a crucial role. So this is a very nice result, and it's a byproduct of the QCD, lattice QCD, that allow us to understand better this strange nature. So the comment is that it is a very impressive result for the accuracy first. For the physico-philosophical content, I mean, we understand why this symmetry breaking, what is the consequence of that? It's not only to make the Lagrangian ugly, but it has a very dramatic consequence. This is like that in order to let the matter to be stable. Of course, this is also impressive because these calculations are really hard due to the Coulomb and so on. But it remains a bit disappointing because if you take only the quark mass as they are, as they appear in, not in PDG, but in some group called FLAC, which makes a good recommendation for the physical quantities. So these values, you see, is very ugly. Mu is half of MD. And the symmetry of the world. And if you simply make the sum of proton minus neutron, of neutron minus proton, this is neutron, UDD, you obtain 252, and this is also the result they obtain, 252 practically, doing all the machinery of QCD. So it's something that, of course, I told them to try to understand that, and so understand things a posteriori is always easy, but a priori nobody could believe that things look so simple. Well, now, so this is for the baryon mass, okay? Now related quantities to the baryon mass. What is this? There are two. What is called the sigma term. Sigma term is this average value for pion nucleon, where it appears. This sigma term is the slope of this extrapolation, and this is the reason why I show you. So this is the derivative of this curve at the physical point. Well, it turns out that this quantity, it is measured in the pion nucleon scattering and so on, and also it controls the direct detection of dark matter, if at all, in the space. So John Ellis made a recent paper saying that this is crucial, and the main uncertainties come from that. So this quantity can be extracted from lattice, can be measured, but you will see that the measurements are not very conclusive. Unfortunately, lattice no, but in principle we can obtain the result perfectly well. We are on the way. Now this quantity, which is the derivative of the m nucleon mass as a function of m pi square, we do not agree very well. For instance, in our collaboration, the previous collaboration, we obtained that. BMW obtained that. So let's take only the central values, 60, 40. Another collaboration, 45. Some people said that when they analyze our results, they obtain another, so it's a mass. Now, concerning the experiment, the situation is also similar, because there are two groups of experimental results. One of them gives 45, the other one 64. It looks crazy, because here we are also oscillating between 64 and 45. So it's not yet clearly established. From the experimental point of view, I don't think that there will be progress in the near future. In the lattice, for sure, we will clarify the situation, but each new paper that appears is either here or there. So just to show you that even if the masses are perfectly well, even these subtleties of neutron proton, there are still related quantities to the proton that are still unclear. Now go, where is the break? Now. Okay.
Your lesson, we can also, it depends on you. You can
So I will finish maybe the excited states, and I will start with the glue balls. So the excited states, we can say that we could expect that if the grounds are good, the excited also. No, it's a disaster, in fact. You know, experimentally, for the nucleon, but it's true for the other variants. Experimentally, the nucleon is here, 940, and the first excitation of the same parity is called the Roper, is there, and the first excitation of negative parity is a little bit higher. And we are unable to reproduce that, by far. Not only we, I mean, this is a well-known fact on the quark models, on the non-relativistic quark models. All of them gave an inversion. Not all. I will show you one of them, that, but practically everybody. So but of course, models are models, and people remark that it's unpleasant and so on, but okay. But QCD, lattice QCD is doing the same. This is more. So, for instance, here, in the quench case, this is also to show you how the approximations can be bad things. 10 years ago, everybody was doing only quench approximation. So this determinant was set equal to 1. Of course, it's more easy. And there was this group who said the following. They compute the nucleon mass as a function of the pion mass, or the quark mass for the nucleon. And they said that, in fact, there was a kind of inversion. So this is the nucleon, this is the Roper, the negative parity, and there was an inversion, and this bad situation that doesn't reproduce the correct order was inverted when the pion mass was smaller, and there was a large excitation. This is related to the chiral transition and Well, unfortunately, it is not true. So when people take seriously the quench, the unquenched, the determinant, all the result was not confirmed. No, it was infirmed even by Grass group. So there is nothing. There is no any inversion. They was from foreign states. I don't remember. Liu and from Kentucky, no? Yes. The results were correct. What was wrong was the quench approximation. So we took seriously something that seemed reasonable, but it's not. And then I think the first group that found that this was not true was Lang and Gadringer, the Grass group, because they are always interested in the excitations, so they infirm this. And the problem remains. It's still there. So, and this is very worrying. Now, well, this is just to tell you that in some quark model, in Grass group, the so-called chiral quark model, they reproduce correctly. So there is a quark model in which the quarks interact by pion exchange, but nevertheless, se non è vero e ve ne trovato, they reproduce nicely. This is the Roper, the excitation of the nucleon, and the first negative parity is higher. To my knowledge, it's the only, to my knowledge. It's not the only, okay.
And moreover, if you see let's say, the original version of that model, which is not numerical, but it is analytical.
Analytic?
Yes, there is not
No. The very first one, there were also this Finland guy, no?
It's, I give you the name.
Okay.
It's a Russian guy.
Russian?
And you understand that the inversion is due to the presence of the...
Pseudo-scalar exchange.
Yes, exactly.
Yeah.
That's Mason degrees of freedom.
Yes. Yes.
But as I told you, it can be obtained
By another method.
also with other...
Well, you will give me the reference, because for me this is the only...
No, it's not.
The only...
And if you want to understand the reason, as I told you, you have not to see the numerical results. You have to see the analytical model.
But nothing is analytic when you compute the three-body...
No, sorry, it's harmonic oscillator plus this Gaussian-Boson inspired term.
Okay, so...
They used this, let's say, SU6 breaking term.
Yes.
Coming from with a spin isospin, or if you prefer, lambda. The lambda.
Lambda, what is lambda?
The matrix, SU3 matrix.
The Gell-Mann matrices.
The Gell-Mann matrix. But if you restrict yourself to the non-string sector, is essentially spin, isospin, and spin, isospin. So it's simply that they have more parameters.
Yes, they have more, that I agree.
And if you increase the spectrum, so you don't consider only the first excited shell, let's speak like a shell model.
Yes.
If you go up with the energy,
Yes.
it's a mess.
But yes,
It's only a fit,
is a fit, but si non è vero viene trovato. In any case, lattice cannot reproduce that. But I am interested to have other references because when I give these seminars, it's better to be complete. Well, so this is the inversion. So this Sheng, Dong, and Liu, and so on. This is the Roper, which was higher than the negative parity. There has the inversion. This is what has been not confirmed by Berns, Graf, Regensburg collaboration. It was very nice because it was related to the pion mass and so related to the chiral, but sometimes nice things are not good. Well, this is the last results. I took it from some collaboration in which indeed they found the same problem. The only, this is from, I don't remember the name of the collaboration, but Bulava, Morning Star, I don't remember. What is the name of the collaboration? Is LHPC? LHPC maybe? Okay. Which is the most complete for the excitation of values and so on. So this problem, the only feeling we have is the following, and it was also pointed out by Lang, is the fact that if we include not only the three quarks, but the possibility that this baryon decays into a nucleon plus a meson, then the real part of the energy is shifted dramatically. This is the only hope. Why it is not the solution? Because he was not able to do it for the Roper itself. It was noisy and so on. He did it for a negative parity state. So the other resonance. the pion.
No, just to
Yes,
say,
yes, yes,
because,
yes.
otherwise it's some confusion because on one side you say it's perfect. Then on the other side, no,
We can move.
we can move the mass of the pion as
Ah.
one should say. In that case, it's a meter in some of your quark mass.
Yes, yes.
Something sounds strange, but just to point out.
Okay. So I have to make a comment following a suggestion of Gianni that in some plots you have seen that the m-pi is a parameter. This is a question. So we compute everything as a function of m-pi. And on another hand, I said that we reproduce perfectly m-pi. So there is something that it is not clear here. It is not clear because both things are true, but they are not used in the same way in each of the situations. When we want to, so the comments are the following. If we want to really say what is m-pi, the m-pi that we are able to reproduce, we make m-pi as a function of quark mass and see if it goes, the extrapolation goes to the physical value. Then is when we know that the pion is well reproduced. When we compute m nucleon as a function of m-pi, in fact is a way, a lazy way, or a clever way, I don't know, to do it as a function of mq, but mq nobody knows what it is. So we never know if we are close or not to the physical value. Well, when we reproduce as a function of m-pi, and we said that m-pi is 300 MeV, we know that we are not simulating the real theory, but we are far. So this is why we play with m-pi in two different things. There is another question about the lattice spacing, but I will not open it because... So you have to give me 3 more hours next year. So go to glue balls. This is a very fascinating object because QCD predicts a lot of things that are not observed. Tetraquarks, hexaquarks, hybrids, QQ plus gluons, and none of them is really identified. The most exciting prediction is where there are no quarks at all. I love this thing because it is, I mean, what is the Higgs contribution to these objects? And this is the most how to say, non-canonical prediction, and is the one that we are really sure that should exist. So this is the most serious calculation in lattice QCD, quench, and it's not the Middle Ages. So they compute this gluon, this glue ball spectrum. You see that this is JPC, different J and parity, JPC. So for different JPC values, there is a rich spectrum which is unambiguously predicted. Here the mass are, here is the mass. So it's about 1.7 GeV. So there should exist an object which is twice heavier than the proton, with no quarks at all. Of course, it can decay, and it's not clear how long it will survive, but it should exist. Now, no one has been clearly confirmed experimentally, as it was already commented by Professor Pennington, maybe, or at least in private communication, because there are mixtures with other states and so on. But this is something that it is there. I mean, not only one, but several states. Now, these are quench calculations. And we already know that in quench calculation, even if the calculations are right, the conclusion is not true. So the question is how reliable they are. And the answer is a little bit poor, in the sense that there is only one unquenched calculation. And so this is terribly. But these are the fair results for the unquenched calculation with m pi equal to a large value. It means that the quarks are large, but who cares? We are talking about glue balls. Glue balls appear on the quark, but only through this. So we cannot expect. But okay, and what is the conclusion of this terrible table? It's very simple. Is that the ground state we show, this one, survive. This is. So in the Pearson and Morningstar, it was predicted at 1.7 GeV. There are another prediction here, 1.7 GeV. This is wrong everywhere, so no. And the unquenched result is 1.7. Let's put 1.8, but okay. So this remains. Now, we can always believe that Debye is behind, but I mean, for the order excitations is not true. Look, for instance, this one, the 2++ already oscillates a bit, not terribly, but 2.6, 2.4, 200 MeV. Here, 3.7, 2.6. So the other excitations on the spectrum are more or less questionable by this unquenched result. For instance, here also 3.4, 3.1, and so on. But for me, what is important, the main conclusion is that the 0++, the lowest glue ball, should be there. Waiting for better, because I mean this is already a relatively recent result. I've not found another one on glue balls. So this object should exist. How to find that experimentally? This is a great question, but it's something that, contrary to the tetraquarks and other systems, not to talk about pentaquarks and so on, this animal is robust. Okay. I will not take about models because they adjust the parameters to the lattice results. So the predictivity of that, it is, I mean, this model, well, they will not talk. Now, what I will talk about a bit, just to tell you that there are many variants that have not yet been observed and that has been predicted by lattice, those containing 2C and 1S, 3C, and so on. So this is one example of, well, maybe this one has been observed, but there are some of them that are predictions, unambiguous, okay, predict for exotic variants. So we can we can obtain some strange masses, for instance, for omega CCC. It's clearly. These are the kind of plateaus on the effective mass as a function of time. You see that what I show you is so nice for the nucleon. When we go to the a little bit strange baryons, this plateau is a little bit in our imagination, but okay, it seems to exist. It should be very important to kill all that, to have it before. This is the signal to noise problem that appears here also dramatically, but okay, we can make predictions with no any parameter. I remember you that this is a theory with 2 or 3 parameters, here 3. So now let's go a bit further. So I have to stop at what time? Let me... Around 1. So what do you want? Because we have 20 minutes. Because I have... because I have results on different things, on finite temperature, on the Yukawa project. Okay, I have to reach at least the Lecture formula because I give you an exercise. It is in the notes. It is written in red. It's an exercise in which you can do at home, test the Lecture formula for the scattering. So at least I have to reach this point, because if some of you are interested in doing that, is a very simple calculation. I can help you by email, or just you come to Paris when the weather is good, and we will continue. So we can put also 2 baryons on the lattice by the same technique, okay? 2 baryons means 6 quarks in the initial state and 2 quarks in the final state, and we can solve 2 different problems. One is the bound state problem, compute the deuteron without nucleon potential at all, or compute the scattering on 2 nucleons. We can also solve this problem of one of the exotic states predicted by QCD, which is the so-called H particle, which is a combination of lambda, nucleon sigma, is a strangeness S equal -2. So you take all the baryons that can give by pairs such that S equal -2, you make a linear combination and you obtain the H. The H particle was predicted by Jaffe in the MIT back with a very large binding energy. Experimentally nothing. And several quartz models found it unbound because, in fact, when you have the SU3 flavor symmetry, everybody finds that it is bound. But when you break that, it's so badly broken that both disappears. Well, so it's an open question, and there was this paper in here saying that there is evidence for a bound state, Bon. When you look carefully into this paper, you see that the pion mass was 400 MeVs. So 400 MeVs is very far from the physical situation, and of course you cannot conclude. So the article, which was a PhysRef letters, should not be evidence for a bound state, should be with a 400 MeV pion, because in fact, when you read it, you are convinced that it is not true, because with 400 MeV pions, I mean, life is very different. So the question is, since that this announcement, there has been several lattice groups that try to clarify the situation, and they compute the binding energy as a function of the pion mass, and you see that the tendency until now, of course, you have one calculation that gives you binding energy of 0 plus or minus a lot of things. So the conclusion is nothing. Because how do you want to extrapolate from these points? If you do it more or less naively, you found that the binding energy, is, you find that 7 plus 2 plus 6, which means 0. So, of course, it's a positive result, but when you take into account everything, the conclusion is that there is no conclusion. So, it's an open question. It's a very important one because it's apart from the glue ball, the only exotic that survive. But okay, this is everything we can say. This is the same. This is the same for other groups, for the H particle. Now we can do the same and put 3 or 4 nucleons already. And here the result is, in fact, is always, all the groups found a bound state. Now the binding energy is, here is, you see, this is the binding energy of helium-4. This is of helium-3. So imagine helium-4 is 12 quarks and 12 quarks at the average value of the products of 24 quark fields. So I don't know. Okay. But the conclusion is for everybody the same. So everybody found the first nuclei. It depends on because they compute it as a function of the lattice size, and the conclusion is stable. The binding energy is found this is the physical point, 28 MeV. So here is rather 45, but the pion mass is 0.5 GeV. 500. So it's not a physical point conclusion. But the conclusion is that everybody found a nuclei, a bound nuclei. The binding energy is not yet the good one, but everybody found that. So this 50 MeV could be very well 20, should be 28 exactly, when the pion mass is the good one. You could ask, but why they don't put the good pion mass? Because when you use the pion mass, the real pion mass, the inversion of the Dirac operator is very, very expensive, because it has a small eigenvalues, so the convergence is very slow. And if you want to make this average of 24 fields, you have to have a huge number of conf to make the statistical average. So you need 40,000 configurations, and they are very expensive. So even if these groups are very good, there are 2 groups doing that, one in Japan and the other in the States, around Seattle. So they are strong and serious and so on, but they are obliged to play with pions of 500 MeV. Nevertheless, the conclusion I find very nice, because for nuclear physicists, at least at partial time as I am, to obtain the binding energy of alpha particle, I need a potential that has 40 parameters. 40, all the potentials. Even the modern potentials based on EFT and so on, they make a lot of noise, but at the end they end with 40 parameters as well. The difference is that they have contact terms and nobody knows what it is, but okay. So this is terrible. And here is really a consequence of QCD, 2 parameters, because here mu equal md.
So it's really QCD.
It's QCD pure, yes. It's an atom. It's very beautiful, even if it is not yet on the physical point, because you have to understand. But it's fantastic for me. It's the first nuclei from scratch.
So this is the new frontier of nuclear theory.
Sorry?
This is the real frontier, forefront of.
But nuclear theory is a terrible situation, because, of course, with the lattice we can do helium-4, 3, but we can never describe the calcium. But calcium exists, and uranium we need it for the nuclear plants. And for these nuclei, we could never use that. We have to rely on the nuclear theory. But this nuclear theory is terribly, I mean, 40 parameters should be forbidden.
I expect that the deuterium is perfect.
No, the deuterium is, but the deuterium has another problem, is that it's 2 MeV. So look the error bars. The error bars, this is 10 MeVs. So not only the error bars are large for the deuterium, but also is very large. It's larger than an uranium atom, deuterium. So we need first, and also it's very subtle in the sense that a small modification of the pion mass can change everything. The scattering lengths are resonant for nucleon, so it's very fine-tuned. So I am not, people compute also nucleon scattering lengths, but with pions of 500 MeVs are totally out of the. So helium-3 and helium-4 is 30 MeV, which is already acceptable. I remind, helium-4 is smaller than deuterium, so it's more easy to compute on a lattice, even if you have a lot of. Okay, so I think this is, for nuclear physics, is very exciting. The same. Okay. Now scattering states. So there was a so-called no-go theorem. No-go theorem means that from now on it's better to stop. And life is full of no-go theorems. Just in France, for instance, I remember when I was young, last century, there was a very good guy, this Dejean, who got a Nobel Prize, who said everywhere, because I was in the seminar, that the superconductivity at high energy is forbidden. And any laboratory in France who applied money to found materials that was quoted and disqualified. Then some years later, one lab from Bell or from IBM, I don't know, a kind of marginal, found a superconducting material at high temperature. The lesson is clear. You should never pay attention to what people say, especially if they have a no-go theorem. Well, this was also a theorem from Dejean. Now, there is also, in lattice QCD, we have always been surrounded by no-go theorems. One, when they found these multiple poles on the naive fermionic action, they said you should stop. Okay. Then there was this one who said scattering is forbidden because if you change the metric from Minkowski to Euclidean, in the infinite space, you lose the information of the phase shift, of the S matrix. So there is no phase shift, there is no scattering. And the result is exact. But the consequence is not true. Because, in fact, on a finite lattice, you could say, but lattice is a way to simulate the continuum. So if something is forbidden, it should be also forbidden in a final lattice. It should be even worse situation, but in fact, it's not the case. On a final lattice with periodic boundary conditions, furthermore, a scattering is impossible to imagine because I have periodic boundary conditions. So if I go there and I try to escape, I return and there is no scattering. A lattice is a crystal. If I put two particles here, they are also here, they are also here. So on a crystal, so scattering was difficult. Nevertheless, if you put two particles on a lattice, they have a binding energy. But this binding energy, if it is not a bound state, if it is a bound state, you increase the lattice size, and they remain as they are. They are bound, so doesn't matter. But if they are not bound, it happens that they want to escape, and the binding energy depends on the lattice size. And this dependence has information of the scattering in the infinite space. It's totally crazy. But it's true. And this was pointed out by Lecture, and this is the exercise I give you. So he said that the energy levels of two particles, you put two what you want, two pions, they have some energy, but they depend, if they are not bound, the energy depend on L. And from this dependent, you can extract the scattering. The simplest example is that I consider the ground state of these two particles, okay? And the dependence of L dependence of the ground state of these of the energy of these two particles is related to the scattering length in this way. This is an expansion, but it is a very clever expansion. It means that if the scattering length is smaller than the lattice size, with one term, with that it is enough to get the scattering length. If not, you have to add that. And more clever is that these two coefficients are independent on the interaction. This is incredible. Doesn't matter if you do a non-relativistic calculation or pi with full QCD, doesn't matter. These coefficients depends on the geometry only, on the geometry of the lattice. In fact, sorry? Yes, on the lattice point, in fact, on the number of lattice is no coefficient. So the conclusion is very easy. You take two animals and there you compute the binding energy as a function of L, and from this fit you get the scattering length. Of course, when you do it on a lattice problem, you have no real control. I mean, because pi scattering length in some channel is not very well known, and if you do phi, I don't know, k pi and so on, I am not sure that the experimental is well. But the exercise I propose you is for a non-relativistic system for which you know the exact solution. So you can see how well this is reproduced. What I suggest you is to take into account a three-dimensional box, two particles on a three-dimensional box with periodic boundary conditions, and in addition you propagate this system in a Euclidean time. I give you the equation, it's very easy, and if you propagate whatever state you want, doesn't matter. All that, at the end you will also obtain some coefficient times the ground state. Not only the ground, but also the excitations. So this is a way to solve the three-dimensional Schrödinger equation using the same technique that lattice. Periodic box, three-dimensional box with periodic boundary conditions, Euclidean time, Euclidean correlator, what I propose you also, exactly the same. So you have an effective mass, you see a plateau, and well, enjoy life if you want. So you can compute not only the scattering length, but also the phase shift. And it could be interesting to do it in momentum space. So if you convince somebody from the audience. These are some results now for lattice QCD already for the pi-pi, isospin 2 pi-pi scattering. So these are the pi-pi, pion-pion phase shift as a function of the momentum. So you see that people is able to do it. This is 2000 what? 2000, I don't know. CP-PAX collaboration, okay, I don't know. But we are able to compute these kind of things. We can also compute the rho, decay of the rho. These are some examples. I don't want to insist because I want to make just a comment on nucleon potential, because people use lattice to obtain a nucleon potential and claim that this is the the truth for the nucleon potential, because it comes from the lattice. It's not true. In quantum field theory, a potential doesn't exist. There is never a potential. When we use a potential inspired by Yukawa, for instance, we have a Lagrangian which gives us this vertex. We put another vertex here, and we identify this amplitude to the potential. And then we insert it into a Rodinger equation and patati patata. And in fact, we obtain indeed a sum of these kind of things. And all our dynamics is given by this sum, called the ladder sum. But this has nothing to do with the Lagrangian, nothing. Especially, it is true that for QED has something to do, because alpha is 1 over 137. But when alpha is 1 or 10, it has nothing to do. So a potential in quantum field theory doesn't exist. So how these guys manage to do that? In fact, just to tell you, because this is concerning the interaction, the nucleon problem is very complicated, because the nucleon is complicated. And look, a nucleon is a cathedral, and what can happen in a collision is terribly complicated. If you want to mimic that by a point against a point with something, it is not rare that the price you have to pay to make this terrible simplification is the following. You have to add, I don't know how many diagrams, some of them are divergent and so on. So this is the nuclear physics. Now, how to get a potential from lattice QCD? There is a recipe, a protocol. The protocol is the following. They compute something that is well defined, which is the Bethe-Salpeter amplitude, which is defined as an average value, not vacuum expectation value, but this is two nucleons, two nucleon state, and this is a quantum field theory, indeed, quantity. So it can be computed on the lattice. Now it can be computed on Euclidean. And you see that in Euclidean, with Bethe-Salpeter equation, there is no scattering in Euclidean. It is not possible. Gianni can explain you why that. But they take it as it is. Then they identify that to the Rodinger wave function. Of course, this is a relativistic object. It depends also on the K0 component, but they remove it. And what remains, they said, this is the Rodinger equation, the Rodinger wave function. And then they do the following. Of course, if you have the Rodinger equation, and you know that the wave function, that it is identification of that, fulfills that, and you know psi and the energy, because they put the two nucleons on the lattice, so they know the energy, they say that V is, you can say that V phi is equal ta 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 ta. So they obtain V in this way. And it works. Indeed you find the V. But there are some refinements, I mean a little bit, but essentially they do that. More or less dressed, but... And they found indeed some nucleon-nucleon potential, so these are the results. So I would like just to point out that of course, they don't found a Yukawa tail also, but that doesn't matter. So this is a protocol to obtain a potential, but a potential, I mean, if you have another protocol, you will obtain another potential. A potential is not well defined in quantum field theory, so this game can be, as a game, interesting, but as a physical contents, I am a little bit out of my shell when I... Okay, so it is, I would say, a qualitatively important result in the sense that they found a repulsive. But the repulsion is because they put quarks together. So they found really a repulsive core here. This is the potential as a function of R, a very strong repulsive core, and so on. But the ambiguities of this method will be always greater than the required accuracy in nuclear physics. There is no way to escape. I mean, we are always 20 MeV of uncertainty. In nuclear physics, we cannot do these kind of things. So the nucleon, and they are badly needed in non-relativistic quantum mechanics if we want to do nuclear physics, unfortunately, would rather be provided by conventional methods. I mean, this approach cannot give you that. Another thing, much more serious, is the phase shift, because phase shifts are really observables. They are defined in quantum field theory, are the exponents of the... And this can be, using the Lucius formula, unambiguously predicted. And they are on the way. They have some results, but with large pion mass. Look, 700, M pi 700. This group wants to be pioneer, they are, but it's nothing, the physics is not there. But they show that technically it's feasible. So we will get the nucleon-nucleon phase shift totally unambiguously independent of the potential, which is... and that is in the coming years. For the nucleon, one can say, but we already know that, indeed. But there are systems that we don't know, and that we will never know. For instance, hyperon-nucleon and mainly hyperon-hyperon interactions. There is no way to have an hyperon beam and to get the phase shift. So lattice QCD could provide this result without any ambiguity. Phase shift. Another thing is the interaction. The interaction, everybody can invent their own interaction, provided it reproduces this phase shift that will be the true ones. So this is, for me, a very important point. Well, I think I have to stop, no? Is it? Or I have other things and finite temperatures. No. my issue is this exercise I submit to you if you want to do it. Is interesting because we will use the same technique than lattice. You will end with a program that gives you the three-dimensional solution of a Schrödinger equation propagating through the Euclidean time. And I think if I open another topic, we will be totally out of time.
Professor, because it has shown that the lattice QCD is feasible and also in a critical way, that is not so difficult to approach.
No, it's not so difficult. And now it's in a very interesting era because there are no more no-go theorems. There are things that I couldn't enter. For instance, I didn't say a word because of time about the structure of the nucleon. I have 50 transparents about for instance, the proton radius. We are unable to reproduce the proton radius. If we compute as a function of the pion mass, we lose it by a factor 2. Until a pion mass of 280. Then when we introduce a smaller pion mass, either we lose the proton radius or we lose the GA, the axial coupling constant. So the situation is not at all under control. And this should be clarified. So there are many open questions. There are also applications of lattice techniques to other theories than QCD. For instance, if you want to understand the difference between a Lagrangian and the potential that is inspired by the Lagrangian, you can solve this, for instance, the Yukawa theory on the lattice and see how different they are. So it's plenty of room to do physics.
Let us thank the lecturer, and in particular Mike and Jomer, for really a very interesting, brilliant lectures. And I hope that those lectures will stimulate your work. And more, let us thank all of you for coming. And I hope that your interest was attracted by so beautiful lectures, and I hope that some seeds that you got during this week will stem with next spring. And okay, and I hope also that you had fun, because you were really very a very compact system. I saw that you had a good time, and so. And I hope that it will, so this week, produce exciting results for our community. Thanks to you, and have a buona fortuna.
And a good weekend, no? Because they return next week, no? They return next week. They are here next week as well, no?
Yeah,
they are
some
here.
of them.
Some of them.